Well, Mr. Sams,
Yeah.
I understand that you had a hot prom date when you were in high school.
Well, I got a picture.
You have a picture.
Yeah.
She wasn't a hot prom date?
No, she was.
Oh, she was.
She's a friend.
Just a friend.
Good friend,
Yeah, I had a friend too.
Yeah.
Yeah. Why are we talking about proms when we're talking about, like,
Because we're talking about kinetics.
Yeah, and so, like, how's the best way to get a date for the prom?
Well, you use the laws of kinetics and you can get a date for prom.
Right, you have to, like, hit girls, right?
You do,
Yeah, and knock the books out of her hands.
Mm-hmm.
You guys all know this. If you're watching this on internet land, you've got to get the How to Get a Date for the Prom video.
Yep.
Yeah, it's really very good because we have this great theory on how to get a date for the prom.
It's good stuff.
You know, speaking of proms, I understand that you have a picture for
I do,
me
yeah.
of you when you were 17 or 18 or
Yeah,
whatever.
I would have been, 18.
18-year-old prom picture.
1995.
1995.
Mm-hmm.
Okay, well, folks, I think we need to look at this prom picture. So here it comes. Don't
Actually,
be too shocked.
Don't we have the agenda first?
I don't
Or
know.
is it the picture?
I
Let's
guess
find out what magic.
The magic of
Clicking the pen.
that I can't get it working today.
Oh, it's the agenda.
Well, I guess today we're going to talk about these things, but I still think we should look at the pictures. I think they really want to see the pictures of
Okay,
you
let's look at the picture
at
first.
your prom.
Yeah.
There he is, Mr. Sams Galore, with the pretty young lady right there.
Yep.
He didn't marry her, so
Nope.
Yep. And he's still got the little goatee beard thing going on there.
Yeah.
Yep.
A little something. Like the hair.
The
Isn't that nice?
hair is
It's good stuff.
amazing.
Now, you can't really see it real well in this picture, but that jacket is this crushed red velvet with this black, like,
Red
vine.
velvet.
It's like this vine leaf pattern going through it. It was the coolest thing in the world. Let me tell you the story about the jacket.
The jacket,
I
okay.
played my trumpet in our community orchestra,
got
and the
the
conductor wore this thing to the Christmas concert. And afterwards, I said, "I must have this jacket. Can I borrow it for prom?" He said, "Oh yeah, sure. Just make sure it's clean when you bring it back." And so he lent it to me, and it was amazing.
There he is with this trumpet.
Yep. Ta-da. And yeah, so then that's Maeve. Maeve. Yeah, she's a saxophone player. I think she teaches at some college out in Boston now. Teaches
Wow,
saxophone,
fancy.
and she was a swimmer. She's a really good swimmer.
Yeah, well,
Anyhow.
yeah. You know, I went to the prom too when I was
Oh yeah,
young.
yeah. I
Lucas
understand
Snuffer.
you brought your picture as well.
Yeah, my picture. Well, guys, yeah. Well, my story. Jenny James was my date, and she's a cute little gal. And yeah, well, let me just say that I went to school a long time before you, and red velvet was not in. However,
Well, it wasn't exactly in 95. Oh,
1982.
wait, before
Oh.
you go, this is the year we rented a school bus. Me and a whole bunch of my friends, we rented.
School
like everybody
bus?
goes to prom in a limo. Let's get a school bus and do that and show up in crazy.
A yellow school bus?
Oh yeah,
Oh,
bright yellow.
bright yellow.
It was great.
I
Had a
used
blast. We had
my
so much
dad's
fun.
car. And of course, this would be me in the white tuxedo.
Nice.
Is that the coolest thing you ever saw? The white tuxedo
Something like that.
with tails. And you
With
can see there.
tails,
You got
nice.
the tail thing
Oh,
going on. They kind of
yeah,
come on the
yeah,
backside.
yeah.
Yeah. Not
Very
very
nice.
clear picture, but oh well. Beggars can't be choosers. That's all we could get.
That's nice.
Scanned in from a cell phone or something.
Mm-hmm.
Wow. And there was Jenny right there. Yeah. She's a cute little gal. Yeah. Okay. We should move on. All right.
Yeah.
To talk about reaction rates. Hey, reaction rates is how fast a chemical reaction takes place.
Mhm.
So we're starting today the study of the speed of a reaction. All right. And so if you've watched Prom Date, it explains kind of how reactions take place via collisions. All right. But we measure the rate of a reaction using some units. What would those units be, Mr. Sams?
It's usually moles over liter seconds. So it's the molarity. It's the change in the molarity in a given amount of time.
Yes, or molarity per second. Sometimes, by the way, you could also do it molarity per hour, molarity per minute. So this is just some
Yeah,
time unit.
some time
but
unit.
typically, we use seconds.
Yep.
Sometimes you'll see minutes and hours and seconds. It changes. Just watch the question carefully. And now, how do you determine, when you're measuring a rate of reaction, so if I've got a reaction A plus B turns into 2C, which chemical do you use to measure the rate?
The one that's most easily observed.
Yeah, it's actually, there's no set answer to this. You use the one that's most easy. The easiest, easy, I-E-S-T, I think I misspelled that.
Yeah,
easiest,
there's no Y.
easiest to measure.
Yeah, so it's something
really
that might
depends.
change color,
Yeah.
something that maybe a gas is being produced that you
Yeah.
could collect, something that observably, I don't know, flashes and makes light. I don't whatever you're looking at that you can measure.
There might be one, say, related to acid-base properties.
Oh, yeah.
So you can
pH
measure pH change of
Mm-hmm.
some kind. You're just looking for something that would be easy to measure using whatever devices that you have available. So color change, gas given off, pH. So it varies from question to question. And so actually most of the problems that you see are not going to do that. All right. Now, so for example, we have a reaction. NO2, two of them, breaks apart into two NOs and O2.
Mm-hmm.
And so in this particular reaction, we want to sort of graph this reaction. So let's say that I had an initial concentration of NO2 of, what number we're going to use? 0.01. So let's say that this number is 0.010. And of course, the amount of NO would be 0 at time t equals 0, and O2 would be 0. So let's make a graph, and if this is 0.010 right here, okay, what's going to happen to the NO2? This will be, I'm going to make a colored lines here, so you should have some kind of a colored line. The NO2 over time is going to decrease. So we'll make the black line the NO2. Starts out at 0.01. Let's then change colors here. How about blue? And now we'll start with the NO. Now the NO, actually let's go back a second. The NO, all right, it's very important to understand that this is a 2 and this is a 2 right here. So for the nitrogen monoxide, because it's a 2 to 2 ratio, it's actually going to increase at the same rate that the NO2 will decrease.
Yeah.
Now that's because, of course, essentially there's a 2 in front of here and there's a 2 in front of here.
Mm-hmm.
However, we happen to have oxygen, which is a different ballgame altogether. Now the oxygen, because in our reaction, if we go back there, there's a 1 in front of the oxygen.
Yep. It only appears at half the rate the NO appears.
So it's going to look more like this.
Yeah.
And this is the oxygen, and that's because there's a 1. So you're going to produce oxygen at half the rate that you will the NO. I'm not sure I drew this perfectly, but essentially if this number is one number, this value here will be exactly 1/2 of this value at this particular juncture. And that's true in every case. I'm not sure I drew it perfectly, but I think you get the idea.
Now, should we talk about the question that everybody always misses?
Yeah, there's a very important question that's often asked in AP chemistry land. All right, let's say that we knew the rate of a reaction, of this reaction, to be 3.2 times 10 to the minus third molarity per second. And this was, what they did is they measured the production. This is the rate of oxygen. Okay? They oftentimes will say, what is the rate of the disappearance? I don't think I spelled that right. Of NO2. How would you go about solving that problem, Mr. Sams?
Well, we know the rate of O2 is 3.2 times 10 to the negative third. I would just look at mole ratios.
So 3.2 times 10 to the negative third molarity per second, but that's of O2.
Right.
Set this up dimensionally, and then what you would do is you would say that there is 1 molarity per second of O2, and there are 2 molarity per second of NO2. So it's simply just the mole ratio.
It's a mole ratio question.
So it's simply just 6.2, double that, right? Times 10 to the minus third molarity per second.
6.4, but yeah.
6.4, yeah. Didn't do my math right. All right. It's just simply, when they give you a question on the AP exam, you try and do some of the stuff we're about to teach you, and you get all confused. It's really a simple, really stoichiometry thing. It's nothing tricky about it at all.
Nope.
Okay. Well, let's move on. Hey, there are 2 types of rate laws. When we study rate laws, these are mathematical expressions of rate. There is what we call the differential rate law.
Mm-hmm.
And then there is the integrated.
Integrated. Those are nice, happy calculus terms, but we're going to do it without the calculus.
Yeah, calculus. Actually, let's go back and talk about what a differential comes from the word derivative.
Mm-hmm.
Now, if you are in calculus, pay attention. If you're not, don't panic. I'm not going to try and convert you to calculus land. This is a curve, right here. Essentially what they're doing is the rate is really the slope of this line.
Slope of the line.
But the problem is the line is not a
curved,
line. It's
right.
actually maybe a better thing is the slope of the curve. But the problem is the slope changes. So when you're at the beginning of the reaction, the slope right here, would be rise over run. But if I were down here, the slope would be something like this. And so, of course, the slope of number 1, if you will, and the slope of number 2 are not the same.
Right. So the rate of the reaction changes as it progresses.
So you guys in calculus land, this is essentially the derivative, which is the slope of a curve. The good news is you don't have to do calculus to do what we're going to do. And actually the integrated rate law, which we just talked about, is actually the integral. So if you've gotten that far in calculus, you understand they're actually using the integral of the curve.
But we're going to do it without calc.
Yeah.
Yay.
So don't panic.
Which is good because, frankly, I'm really rusty on my calculus.
I don't know. Mine's rusty.
I'd
too.
fake it.
I know the concept of calculus, but actually the physically knowing how to do it.
Yeah, exactly. That's kind of where I'm at too. Yep.
So we're going to start with the differential rate law.
Yep. The next podcast.
Sometimes, by the way, it's just called the rate law. So when they say the rate law, they actually imply it's the differential rate law. When they use the integrated rate law, they will use the word integrated. Because the more common rate law is just the differential rate law. So they got lazy and just called it the rate law.
Yay.
Well, the rate law takes this form right here. The rate would be equal to K times the concentration of some chemical A to the power X times B to the power of Y. This would be a reaction where A plus, say, 2B turns into C or whatever the reaction might be. Now, as a side note here, the coefficients here, 2 and a 1, whatever they might be, do not matter in the rate law.
No.
You can only find the rate law. Actually, the rate constant is K. Okay, that's a number. We'll talk about this a little bit later. But the answer, how do you find the rate law? There's only one way. You do an experiment.
Yep.
You can't just look at it. A lot of people want to say, well, there's a 2 here, so that 2 goes here with the Y.
Don't do that.
That's wrong. The only way you can find it, how can you find it, Mr. Sanders?
Do an experiment.
Only experiments.
You have to do science.
Experiments.
You must do
only experiments.
science.
Experiments.
You got to do it.
Only experiments.
Wow, that was weird.
That's a very weird voice. Okay.
I like it. It's like robot.
Robot
guy with weird accent.
Yes, that's pretty fun. All right. That then leads us to the concept of the order of a rate law.
Yeah, wow.
There are, now you can have a rate law that's rate equals K times A. Now if you think about this, this would be to the first power. So we call this a first order rate law. You can have it rate equals K times some chemical A squared. What do you think?
That's second order.
That would be second. Hey, K equals A, rate equals K times A times B.
Okay, there's little ones above the A and the
kind
B.
of like a 1 and 1 apply.
So we're going to add those together. So that one's second order as well.
So you actually just add the exponents, guys. And then you can also, right here, of course, we got a 1 and a 2. That's pretty easy. That'd be a third.
Yep.
By the way, rarely will you get a fourth order rate law. Actually, rarely you get a third one.
And occasionally you can also
most are first, second, or first or second.
Yep.
And actually, there's also a what?
There's also zero order, but we only really
Let's talk about that. Rate would be equal to K times A to the 0 power. 0. But if you think A to the 0 is equal to 1, so actually its rate equals K, and that's called a 0 order.
Yep. And yeah, so those
we're actually going to see that in our experiment. We have a big experiment that we do, all-day lab thing. And one of the reactants will have 0 order rate.
Yeah.
Okay. All right. Now, we need to talk about how you determine the units on K. So, actually, let's go back for a second. So if I've got a rate law right here, and I've got rate equals K times A to the first, the K here has a different unit than the K here. I know that's confusing, so let's kind of talk ourselves through this. Now, it all starts with the units on rate. So remember, let's just do a first order.
Okay.
So rate would be equal to K times A to the first.
Right.
So the units on rate, we learned that just a little bit ago, would be molarity per, say, seconds. And that would be equal to K, I'm going to put that in parentheses, times A. Now the brackets, now we know what the brackets mean. What do brackets mean?
Concentration, which is molarity.
So that'd be molarity over 1, right?
Okay.
So I now need to kind of use dimensional analysis to try and say what would go into this box right here so that this right here times whatever equals molarity per second. So what might that be? Let's think this through here. First of all, I need to keep molarity on top because molarity is on top right here. And, well, it is.
Yeah, so it's there. So the top has to be 1.
1. And I need to put seconds on the bottom. It's not here, so I can put it here.
There.
So if I were to multiply this times this right here times this, I would get molarity per second.
Yep.
So that's it. So what are the units on K?
The units on K is 1 over a second.
So the K on this one would be some number. And it would be...
1
Now,
over
how
second.
would you write that?
You could either put 1 over a second, you could put second to the minus 1. It's
Yeah,
probably
usually
the
we would
cleanest
say
way.
second to the minus 1. Or you could have your number, whatever, the number will be like 15 or 10 to the minus third or whatever it might be. So number over second. That's it.
That works too.
So that's for a first order rate law. Now if I have a second order rate law, you would say rate would be equal to K times the concentration of, say, A times the concentration of B. It could also be A squared or something like that. And actually, let me show you a different way to do this. Actually, Mr. Sam's methodology. You would say molarity per second would be equal to K times molarity times molarity.
Yep.
So we're trying to find K. So how would you solve that, Mr. Sams?
Now, I would do this algebraically.
Okay.
Mr. Bergman's method works great. This is just another approach to doing it. So since I want to get K by itself, I'm going to divide both sides by molarity, or molarity squared, whatever you like. Okay, so I'm going to divide that by...
Divide this side by molarity.
Uh-huh.
So
Okay.
molarity cancels.
Right, so K equals molarity over seconds over molarity. Now, we have two denominators there. Okay,
So-
anytime you have a double denominator, anything in that bottom denominator gets brought up to the numerator.
So what you do is you take molarity per second times, what would it be, 1 over molarity squared. Right?
Yep.
Is this not the way you do this?
No, that's fine.
Okay. And then the molarity here cancels, and then one of the molarities cancel here, and what do you get with? You get 1 over molarity seconds.
Yep.
Or we would say molarity to the minus 1 seconds to the minus 1. So you'll have your number, whatever it is. Yeah, I like that method. I hadn't thought about that, Mr. Sams. That works. Yeah. Or if we could go to a third order rate law, so we could say the rate of a particular reaction would be equal to K times the concentration of, say, A squared times B. So you can say molarity per second would be equal to K times molarity cubed.
Yep.
All right, divide both sides by molarity cubed. Molarity cubed cancels, and you get molarity per second divided by molarity cubed. And I like to think of it as two fractions. And then you say molarity per second times 1 over molarity cubed. And that'll be, this molarity cancels, this 3
Goes down
becomes
to
a
squared.
2. Should be 1 over molarity squared seconds, which is molarity to the minus 2 seconds to the minus 1.
There it is.
Yeah, I like that method. I
Yeah.
haven't done it
I kind of
that
like
before.
yours, so
Yeah, mine is more visual, and yours is,
a little more mathematical. Yeah.
yeah, more
Either way works.
mathematical.
Pick
Whatever-
one that you like, whatever works
It
for you.
doesn't matter.
Go for it.
Okay, once you know the rate law, oh, this is just an introduction to the integrated rate law here. This is the integrated rate law. And then you're using the y equals mx plus b. And, you know, we're going to cover this in the integrated rate law section, so I think we're going to skip
just
this
hit
part.
pause in your brain on that one.
Yeah, I don't think they're... All right. All right.
Okay, here we go.
Yeah, let's do a problem. I think there's a thing called the method of initial rates. And basically what we're going to do is we have some data, and we'll show you some data in a minute. And here's the rules. Choose two experiments such that all but one variable cancels out. Set an equation up like this. Cancel all but one of the experiments. Find x and then y. Use one, the average of all, to find the value of k, and use dimensional analysis to solve for the units of k. All right, so let's take a look at an experiment. So here's an experiment. We have ammonium reacting with nitrogen, or nitrite, making nitrogen gas and water. And what we have is they did 3 experiments. They started with experiment number 1, and they had 0.1 molar, and then of the ammonium, and of the nitrate they had 0.005, and then this was the rate. And so essentially what we're going to do is we're going to then do this method to solve this problem. All right, so what we're going to do is we are going to solve this problem. Okay, so what I want to do is take a look at experiment 1 and experiment 2.
Yeah.
Now experiment 2 and experiment 1 have the same molarity for the ammonium.
You always want to start with one that has one thing changing and one thing the same.
And this one changes. In fact, it changes by a factor of 2. So what we're going to do is we're going to say, we're going to take experiment 2. I like to always start with the bigger one.
Yeah, put the big rate on top.
So I'm going to say rate 2 divided by rate 1, where the 2 represents experiment 2,
Yep.
and this is experiment 1. You should have that data table right there.
Yep.
So I'm going to say 2.70 times 10 to the minus 7th. Actually, let me just say one other thing here.
Huh?
This reaction,
Oh yeah, we need to write the rate law.
the rate law is going to look like this. The rate is going to equal to some constant K times the concentration of NH4 positive
To some exponent
to
that we
some
don't know
power,
yet.
let's call it X, times the nitrite, the NO2 negative, to the Y power.
Right.
So this is, I'm essentially going to copy down the numbers from the table right here.
Yep.
So that's going to equal to K times the concentration of ammonium, which was 0.1 to the X power, times
0.01.
0.01 to the Y power. That is exactly what it says in the table. I'm just reading the
Yep.
numbers off the table. Now I'm going to do the same thing. I'm going to divide it by rate number 1.
1.35.
So this is 1.35 times 10 to the minus 7 would be equal to K times 0.1 to the X. It's an X.
Yep.
Times, this is a different number,
0.005.
0.005 to the Y. Now, mathematically, this actually, I don't even need a calculator on
Nope.
this one. The K's are going to be the same number, so they cancel. Now, 0.1 to the X and 0.1 to the X will be the same
They
number
cancel.
regardless of what X is, so they will cancel. However, this number, this term right here, will not cancel, so this will equal to 0.01 over 0.005. Now let me show you something. You may not know this, but when we divide two things with the same exponent, it can be written like that. And then if you get 2.7 times 10 to the minus 7, actually the 10 to the minus 7th cancel.
Yep.
2.7 over 1.35 is just 2. So, in this number right here, 0.01 divided by 0.005, that'd be 2 would be equal to 2 to the Y power.
Right.
Not rocket science.
So
here.
2 to the what power is 2? It's 1.
1. So we now know that Y is equal to 1.
Yep.
So we know Y equals 1. We haven't found X, but we have found Y.
Yes.
So now what we want to do is we want to go back to our table and we want to see if we can isolate the X's. So if we look at experiment 3 and experiment 2, these are both 0.01, and that will cause them to cancel out. And then we can use this term. So, and as a side note, you can divide anyone you want by anyone you want, but it's really highly recommended that you take the big one divided by the small one.
Yeah.
So let's take
You get whole numbers instead of decimals that way.
Yeah, you get experiment 3. Let's do experiment 3 divided by experiment, was it 2? 2. So experiment 3, it's 5.40 times 10 to the minus 7th would be equal to K times 0.2 to the X times 0.01. Actually, not to the Y. We know it's actually the first power.
We know what it is now.
We
Might
just
as well
found
put it in
that.
there.
Right?
Now, that's going to be important. Well, we'll talk about that later. Never
Yeah,
mind.
there's a second example. And then this will be 2.7 times 10 to the minus 7th would be equal to K times, now what's
0.1 to the X.
0.1 to the X times
0.01.
0.01 to the 1.
Yep.
Now what will cancel out?
K's go away.
The K's go away.
0.1 to the 1, or 0.01 to the 1.
Yeah.
Yep.
So
All
that's
right.
it. Now the 10 to the minus 7ths even
Yep.
go away.
So-
So 5.4 over 2.7 is actually 2 would be equal to, now if we take this 2.2 divided by 0.1 would be 2 to the X.
So X equals 1,
X
just like Y.
equals 1. So this is really easy.
Yeah, so let's rewrite the rate law now with the appropriate exponents.
So rate would be equal to some constant K, we're going to determine that in just a minute, times the concentration of the ammonium to the first power. You don't actually put the first power, it's assumed if it's in there, times the nitrite to the first power. So this right here is called the rate law, or the differential rate law.
So a question would say, given the following data, write the rate law.
This would be the answer.
That's the answer, and that's the process you would go through to get it.
Okay.
Do we want to show them how to solve for K?
Yeah, we need to do that. All right. Now, and often, most often, almost every time, they're going to ask for what is the actual value of the rate constant. So actually, let me rewrite the rate law. Rate was equal to K times the concentration of the ammonium times the concentration of the nitrite.
Both to the first power, so we don't have to write it.
Now, essentially what I'm going to do is I'm going to pick one of the experiments.
Yep, doesn't matter which one, just pick one.
Let's take the first one.
Okay.
So 1.35. I'm just going to plug in numbers and solve for K. Times 10 to the minus 7th would be equal to K times
0.1
to the first times
0.005.
0.005
I suppose I should be
to
putting
the
this in my
first.
calculator, huh?
So essentially, guys, you just divide both sides by 0.1 and 0.005, 0.1, 0.005. The 0.1s cancel, 0.005. So K is just whatever the math says that this.
2.7
So K was equal to 2.7
times 10 to the negative 4.
times 10 to the minus 4.
And that second question is always,
What are the units? The units, got to find the units. What are the units? What are the units, Mr. Sun?
Well, it's a second order reaction.
All right, so we got that whole second order. Let me use my method, see if they like my
Sure.
method. So we'll say it's, now this was in molarity per second.
Yep.
Yeah. So molarity per second
That's the units for rate.
would be equal to something times molarity squared.
Yep.
Well, I need to get seconds on the bottom of the equation. So I'm going to put seconds down here. And so what needs to go here? This will be a 1. And if I just put an m right here, then that will cancel off one of these
One
m's.
of those, and yeah, yep. Just like
And then
that.
you get molars per second. So it's going to be, so the units on this would be molarity to the minus 1, seconds to the minus 1.
Yep.
And that would be your answer.
There it is.
All right?
Complete with units.
Complete with the appropriate units. You must have units. No naked numbers allowed.
Nope.
All right. All right, let's
All
do a second example. Consider the reaction of the peroxydisulfate ion. There's a sounding deal. With the iodide ion. And there's a reaction. Got it? Okay. Not a very important to know the reaction. We have saved data for you.
Yes.
So here we have a data. Experiment
Here
1,
are the
2,
questions.
3, and 4. Determine the rate law. Oh, that's going to be... Now, what's the rate law going to look like?
Rate equals K, always.
Times the concentration of the reactants.
Right. So
Which is the S2O8. That's the peridisulfate, whatever that heck's called. To the X power times the iodide to the Y power.
Yep.
Basically, they're going to ask you to solve for X, Y, and K. Look, in fact, determine the rate law. That means what's X and Y. Determine the value of K. Oh, include units.
Ta-da!
And then we've got some C and D questions that we're going to deal with in a minute here.
Yep.
All right.
Alrighty.
All right, so let's look at the data. So you guys have got the data, but I'm going to make the data sort of disappear. Actually, before I do that, let me pick two reactions. Now, if I take experiment 2 and experiment 1, they have O36 for the iodide. All right. You know, in this reaction, do we have a, what is this the rate of?
Does not tell us. So whatever is observable, probably that I3 minus ion, because you can detect that with some starch.
So this would be
black.
rated to the I3 negative. That's going to be important in
Yeah.
this question later on. Okay, yeah, let's just take experiment 2. I want 2 divided by 1 because this is 27, this is 18. You'll see that'll make life a lot easier. So experiment 2 divided by experiment 1. So E2 divided by E1, if you will. Experiment 2 is, I don't know where I got this number here. All right.
You have to plug in the exponent.
So if I take experiment 2 divided by experiment 1, I'm going to
Okay.
get the rate of, what, 3?
3.9 times 10 to the negative
So
6.
3.9 times 10 to the minus 6 would be equal to K
K.
times the concentration of the first chemical, 0.018,
0.027.
0.027 to the X times
0.036.
0.036 to the Y. And experiment 1 would be
2.6 times 10 to the negative 6.
2.6 times 10 to the minus 6. So that equals K times 0.018 to the X times 0.036 to the Y. Now I
Okay.
can see that
Let's
my
do some canceling.
ink color, the K's cancel, the 10 to the minus 6 is cancelled. That doesn't always happen, by the way, and these cancels. So what's 3.9 divided by 2.6?
1.5.
1.5 would be equal to 0.27 or 0.027 by 0.018.
1.5.
Oh, 1.5 to the X.
So
Well, X, folks,
X is 1.
is 1. That's pretty easy, isn't it? All right, so we found X. Let's see if we can then go back and figure out how we can find Y. Now, here's a problem. I don't have any two numbers. These are the same, right?
Right. And you always have to start with one that are the same.
But I don't see any of the same over here, Mr. Sanders.
No, and it doesn't really matter because now that we know what X is, we can just plug that in.
So let's
and the
do,
math with
like,
that.
say, 4 divided by 3.
All right, 4 and 3 it is.
Let's do 4 and 3. You could pick any one except 2 and 1.
Can you go back real quick? I want to just make sure I have a correct number somewhere.
I hope so, yeah. I think it's right. All right, so we're going to do, what did I say, E4?
Yeah, hang on a second.
Okay, Mr. Sam's caught an error. So this number is wrong. This is a problem right here. This is 10 to the minus 5. We'll actually fix it on the handout, so probably you won't make a notice, but we just caught it while we're solving it here live. So that makes a difference. We're still going to do 4 divided by 3. So if I take experiment 4 is 1.4 times 10 to the minus 5 would be equal to K times the concentration of 0.05. Now this is to the first power.
Right.
We know that already.
We know that from the last one.
Times 0.072 to the y power. And I'm going to take that and divide it by
7.8 times 10 to the negative 6.
7.8 times 10 to the minus 6, and that would be equal to K times 0.036 to the first power times 0.054 to the y power. The K's are really the only thing that cancel here. Not even the 10 to the minuses. So take, Mr. Sanders, so it's 1.4 divide 10 minus 5 divided by 7.8 times 10 minus 5.
It's 1.79.
So that's 1.79. Not a pretty number. It's not like 2 or something like that. Okay, that's equal to now 0.05 divided by 0.036.
That's 1.39.
And then that's going to be times this term. What's 0.072 divided by 0.054?
1.33.
1.33 to the y power. We're trying to solve for y. Well, we have terms. If we divide both sides by 1.39,
we get 1.29.
All right, the 1.39 cancels. So
1.79 divided by 1.39 is 1.29.
So 1.29, I'm rewriting this, but I'm going to try and keep it on the screen, would be equal to 1.33 to the y power. Now it's not exactly perfect. It is an experiment after all.
It's an experiment, and we did some rounding here. If I had carried out 4 significant figures, those two numbers might be closer to each other.
But so y really is it's 1.
It's 1. It's close enough. Again, it's experimental, so it's never going to be perfect. But we're looking for whole numbers here. That y is not going to be
actually,
like 1.25.
That's an important point to make, guys. That when you're doing these x's and y's, well, they're whole numbers. There is a very rare instance where you could get to the half power, a square root type deal or whatever, but it's very, very rare. So in the AP test, I've never seen it done, but it does happen in real life. Okay, so now we want to just say what's the rate law, right?
Yeah, what is the rate law?
Rate, it's a 1-1 like that last one. So rate is equal to K times the concentration
of
S2O8 to negative to the first times
I minus.
Is it I negative?
Yep.
Okay, sorry. Times I negative to the first. They're going to ask us now the second question.
What's the value and units of K?
What's K? All right, well, let's just pick an experiment.
That's
How about like experiment
1?
I like to use 2.6. Actually, if it was a true experiment, what would you do, Mr. Sanders?
You'd do it for all of them and average K.
Yeah, you would do them all of them, and you'd get slight, and that's equal to K times, what was it, 0.018 to the first times 0.036 to the first. Divide both sides by the 018 here and the 036, and you get K to be
4.01 times 10 to the negative third.
And this would be the same units, by the way, which would be molarity minus 1, seconds minus 1. All right. Now, I think there were a couple other questions.
There were 2 more questions.
So let's go back to those questions. So we've done questions A and B. Question C, how is the rate of disappearance of the S208 related to the rate of the disappearance of the I negative?
All right, we just need to go back to the balanced chemical equation for that.
So which ones were we asking about? This?
Yep.
Okay. So this is very important. They're actually just asking about the coefficients. We alluded to this at the beginning of the podcast.
Yep.
So they're related in that the disappearance of the this S208, it's thio something. Peroxydisulfate is going to disappear
1/3 as fast as the iodide.
1/3 as fast. Or I might say it this way.
Iodide goes away.
Iodide disappears 3 times faster than S208 to negative. Okay?
All right.
All right. And then there was another question, I think.
There was.
What is the rate of the disappearance of iodide when the S208 is such and such and the iodide is such and such? So what are we going to do there?
Plug and chug. Go back to the rate law.
Yeah, so we just go back to the rate law. Actually, let me write this down because we can't see these screens. That's not right over here. Okay. Let me get a balance right here. Actually, we'll go back. I'm not going to jump to that podcast yet. So we know our rate law. But our rate law is this: rate would be equal to 4.01 times 10 to the minus third.
That's our K value.
Molarity minus 1 seconds to the minus 1 times the concentration of the S2O8 to negative.
To the
There should be
first.
brackets actually to the first times the concentration of the I negative to the first. So we know this number and this number. We just plug and chug. So I take 4.01 times 10 to the minus third times the concentration from that problem, 0.015 to the first, times 0.04 to the first.
Yep.
And what do you get?
2.4 times 10 to the negative 6.
And that'd be molarity per second. Bingo.
Ta-da!
Not terribly difficult, guys. It's just a matter of some math. That's the method of initial rates. You're going to do this over and over and over again. Get very good at it. The thing the biggest struggle I've found over years is this solving for the rate units, or the rate constant units.
Yep.
And then this whole business of that tripling thing that we just talked about just a minute ago. Make sure if it's just a simple stoichiometry problem, it's all just about the mole-to-mole ratio. So watch that. Yeah, that's the things I see kids struggle with the most when they deal with this variety of problems. Very, very common question on the AP exam.
Yep. And now that you've seen our prom pictures, send us one of yours.
Oh, yes, that'd be cool. Send us a prom picture. And if you're out there in internet land and you're watching this, you can send it to our email accounts.
Yeah, you can find that, I'm sure.
Find it and send it to us, and we can get your prom picture and post it in our room. That'd be kind of cool.
We'll have the prom picture wall, when we do kinetics.
That's a great idea. We got the prom wall, the wall of prom.
Yeah.
Especially if you got your date in the prom methodology.
Yeah. If you use the knock the books out of the hand, hit girls method, we definitely want to.
Definitely, we need to see who you got using that method.
Yep.
What does she look like? What does he look like? I don't know. That'd be very interesting commentary. Okay. Well, thanks. We'll talk to you later.
Bye.